Sound test. Welcome back, everybody. This will be second part of CSES Dynamic Programming section. Let's go indeed. Edit distance. I will stream until the Division 3 Codeforces round starts. Best programming judge platform? Well, Codeforces is the biggest, but I don't particularly like its style of problems, at least nowadays. So I don't AdCoder, I guess. Though also I don't like AdCoder Grant Contest either, because they are too hard. And not... they are specific to... Well, if one platform was to still exist, then it would be Codeforces. I think 1 minute before we start. As always, let me advertise my group classes. Here those are. It starts from €50 per month, where every week you get a selection of nice problems, and the difficulty ranges. Right now it's from like 1200 to 2800. It's a little bit wider than what I provided in the blog. I need to update this. Every week you get problems. After 6 days we discuss them, most of them. And I think it's a good way to practice and to ask questions, an opportunity to ask questions. LeetCode isn't a competitive programming platform, so it's not really a fair comparison. LeetCode is for interview preparation. For me, it's not interesting because I know how to solve problems from LeetCode. I doubt that there exists a LeetCode problem that I couldn't solve in an hour. Maybe I would struggle, but I would be able to solve. In Codeforces, it's completely different. There are Codeforces problems that I couldn't solve in a day because they are just difficult. Sometimes it's because I don't have knowledge. Those are less interesting, but there are also those that are just hard to come up with a solution. Yeah, the ID name you see here, it's Genie. Okay, I think we're 5 minutes into the stream. Let's start. The stream will be 2 hours. For any range of rating, the topics you need are, practice problems and at your difficulty, and you will see the topics automatically. Watching me after 4 years. Yeah, that's nice. Edit distance. Distance between two strings is the minimum number of operations required to transform one string into the other. The allowed operations are add a character, remove a character, replace a character. For example, if you have a word love and you want to create a word movie, you can do it in two operations. First operation is that you change L into M, you have move, and then you insert an extra I here in the middle, and you have movie. We used two operations. Calculate the edit distance between two strings. Strings are of length 5000, which suggests the time complexity of this squared. Obviously, we cannot do it in exponential way. We cannot try all possibilities of where to insert. If we are to use dynamic programming, we likely need to go from left to right, but we are given two strings. So if I try to, let's say, go from left to right for one string, for let's say love, after I modified, maybe inserted, erased, replaced some characters in this prefix already, then for sure it created a prefix of this second string, not necessarily equal length prefix. Maybe here low should be, of course, transformed into mo, but if we have something like this, where it's, let's say, banana needs to transform to bapple, this. As we go through the characters here, A for sure, almost for sure will be erased, then B, we're not that sure, maybe yes, maybe no, then C and so on. After you process few characters of the first string, you want to know into what prefix of the second string it transforms. Of course, it's stupid to transform ABC into, let's say, character X, because it's not here at the beginning. Also, we shouldn't transform this into character P, because it's not here at the beginning. Always we have some prefix of the first string, and it transforms into some prefix of the second string. And this is our state of DP. Arco, I don't today answer questions unrelated to the problems. Let's read both. I will call them A and B. And for convenience, I will make variables equal to their lengths. So I wouldn't need to always type a.length, b.length. The state of DP will be ij minimum number of moves, because that's what we minimize, to transform and transform. And now we have a decision of what this exactly means, whether it's the first I characters or the characters up to position I. I will say that this is to transform first I characters of A into first j characters of B. That will be my definition. And I'm doing this on purpose so that I would have a starting state. 0 characters I can transform into 0 characters with the number of moves equal to 0. Everything else I will set to infinity, saying that so far I don't see how exactly I should do it. Let's make an infinity variable. Yesterday we did some easier problems, because this is the 10th problem already from the dynamic programming category on CSES. Yesterday we saw already a few examples where we used infinity a little bit. I need this two-dimensional array, dp of roughly size A, maybe something, by B, again maybe something, by default filled with infinity, and only this is the starting state. If I transform 0 characters from A into 0 characters from B, that's possible. At the end, I want to output what is number of moves required to transform the uppercase A into uppercase B of characters. This already suggests what should be here the dimensions. That's like that. It goes from 0 to A. And now the transitions. I will do the standard push DP. This I will leave here question marks, because it's not clear what we should do. I already know dp of ij, the number of moves required to transform the first I characters into the first j characters. So if this is the string A, this is the string B, then what, let's say, dp of 2, 4 represents, what this represents is transforming those, this, let's say, xy, into this, let's say, xyzv. Number of moves required to transform this into that. The next move for me in this process, as we go from left to right, is to decide that maybe this character should be transformed into this one, or I can also erase it, I can insert something. So let's consider all three possibilities. This is my input string. I can insert now something. Why would I insert? Because it's the same as this character here. If this is, let's say, character I, then here I can insert an extra I. I will then have a situation where the first two characters of A I transformed into the first 5 characters of B. So the insert operation, or add/insert, with that I move from dp of ij to dp of ij plus 1. Then there is erase or remove operation, where I have this string, and from the input string I decide to erase the next character, which is this one. Then the current situation is that those 3 characters transformed into those 4. Maybe this one was unnecessary. This is character I, which I do not need here. So I decided to erase it. Then the state describing my situation is those 3 characters I transformed into those 4. I'm done with those 3, and I'm done with those 4. I need to only focus on the remaining parts. And finally, replace. I can look at this character and I can replace it to something. Obviously, it will be the next character I need there. If this is, let's say, U and this is M, I can change U into M. Then the situation is that the first 3 characters of A I transformed into the first 5 in B. This changes this state into this one. I dealt with the first I characters, now it's the next one as well, and I obtained the first J characters of second string, and now I have J plus 1 of them. Now for the actual lines of code, this means dp of I j plus 1 is equal minimum of itself, comma dp of I 1 plus a single operation of insert. This means I'm doing the insert operation. I will do a lot of such lines, and just like in some other problem yesterday, I'm going to make a helper function that applies the minimum. First number, it minimizes with the second one. So this actually should be minimize this new state with myself plus 1. Because I will repeat this few times, actually, I like to make a variable to represent my state. I know that this is number of moves required to achieve this, to transform first I into the first J characters of B. And I will then, in my old transitions, I will just type this. This is, I think, very convenient. Maybe I will leave this as a comment, leave this as a comment, leave this as a comment. And finally, this. So that's my state from I to J. This is my state from I plus 1 to J. And I say, if I can achieve myself in 7 moves, now I'm making the 8th move, so we minimize this with 8. You might notice that this is suspicious right now because I never use the characters in A and B. But, well, there is a situation where I don't need to insert, erase, or replace. And that's the situation where some character agrees. Here O is the same as O, or this E is the same as E. Note that they do not need to be at the same position. But if the first 3 I transformed into the first 4, love with V at the end, I transformed into movi, then E automatically gets transformed into E. So finally I will say match transition, where I can say that from IJ I move to I plus 1 J plus 1, like with replace, but without this plus 1. It's not there because I'm not making a move, though this is possible only if A of something is equal to B of something. And that something is the ith character and the jth character. For example, when we start from I0 and J0, we're looking at the indices 0, and if they match, we can automatically move on. This is actually unnecessary in such a case. So I can even do this, though a moment ago it was also correct. So this is fine. And finally I can, well, optimize the code a little bit, though I'm not a huge fan of it. I can do this. A of I is distinct from B of J. I will call this replace or match. What happened here is that I'm skipping the ith character in first string and jth in the second string, and for that I need +1 operation if and only if those two characters are different. Then I need to replace with the cost of one operation. But if they are the same, then this thing in brackets is evaluated to 0 or false, so it adds nothing. I think that the version with ifs is easier to understand, but you know, you can later rewind the video if you want to look at that previous version. This is, well, shorter. All right, at the end we need to get to AB, so it seems intuitive that we will go up to here, that we go with I up to A minus 1, J up to B minus 1. Another way to look at this is that, so this was one definition, but another one is, now we decide the fate of A of I and B of J. That's also a valid definition. That we are done with characters before I and before J, and now we need to do something with them. Insert, erase, or replace, or see that they are matched with each other. Sadly though, this will not work. Hopefully even for this input. Well, it works, but that's, I think, a coincidence. If I do something like, let me run this on dog cat. Well, that's a free. Dog or OGT. Okay, that's incorrect. Optimal strategy here is to erase D, then you have OG, and insert T at the end, then you have OGT. Two operations only. When you notice such a counterexample, usually in DP it's good strategy to just, you know, simulate stuff on pen and paper or print some stuff in your program and figure out what transitions should be optimal. And here I will tell you what is optimal, but for that maybe I will also draw the two-dimensional visual interpretation of this solution. So we're talking about edit distance. By the way, very well-known problem in computer science. So also on lead code you will find it, in interview preparations you will encounter it. Okay, so there is a way, because we have a two-dimensional DP table, then maybe it makes sense to represent it like that, where if I say D, maybe I will put it here, dog, and this OGT, then what are the optimal DP transitions? What are the optimal DP transitions? When I'm here in this initial state, which by the way should be set initially to 0, everything else is infinity, then I have a possibility of going here, here, and here. Always it's a +1, so you know the values 1 will be printed there. But let's think what is optimal. I should aim to match O with O. So I need to get to this cell. So I claim that optimal path or optimal transition is to there. And that represents erasing D. I start with dog. First I should erase D at the beginning, then I have OG. And that's the step of going down here. So I'm forgetting about D, and now I will need to match O with O. Now, so far the cost is 1. That's one operation, but now O with O I can match for free, and I move on to next character and next character. So O with, because the target is OGT, target OGT in my example. Now O with O is the same, so I can kind of skip them and I can focus on this, G versus GT. So this cell, what it represents is now I need to match G with G, and generally what is remaining is from the G to get GT. What is optimal now? Well, again, to match those two. So I need one operation here. Note that this did not add +1 because O with O were just the same. I didn't need to do an operation. So again, I move forward, and that's something that my code doesn't handle well right now. Because what's now the state? The state actually is something that requires an extra row and column. And what is here is that this non-existing character at the end of dog, I'm matching with T. Also after T there is, let's say, non-existing character there as well. Let me maybe draw this more now as a square. So you can think that after the string there is one more dot, let's say. And where you went to get is actually here. And that matches our code. This works correctly. I want to be left with nothing and nothing. I start here where I need to match D with O. And the optimal path looks like that. Where I erase D, I match O with O, I match G with G. I then need to match something with T, then T needs to be erased or inserted. Inserted because it didn't exist in doc. Actually, insert and erase are symmetrical, it's just that one applies to the first string, the other applies to the second string. Okay, so this is something that adds +1 operation, this is something that adds +1 operation. And if you try to debug our code, what you will realize is that we never get to this state. We are never here because the for loops only iterate those states, and only from those they transition. The only way to get to this target cell is from here by diagonal, which means I try to match G with T and I replace one with the other, which is not always optimal. I need to also allow my for loop to iterate those cells. Actually, my for loop should iterate everything here. In particular, this state, which says that I matched dog into O, and now I need to match something with G. Because when or let's look at another example. Banana with ananas. Or, I don't know, this. If I need to match those two words, then what is optimal is to, I think, erase B. The anana matches with this. And then I'm at the end of this string. I already am done with this. I'm at the end of this string. So you think about it as this dot here. And still I have few characters from the other string to obtain. And that would represent going through here with this row that actually doesn't represent any particular character in the first string. So a lot of vertical steps. So it is possible that in this square or rectangle representing our TP transitions, the optimal path looks something like that, and starting from some moment we keep doing horizontal steps, or we keep doing vertical steps, and that means that we are faster done with one string than the other. So now to fix that in code, I need to here go up to A and up to A, but here then we need to avoid out of bounds errors, which is this is not allowed if J is too big. So I will say if J is not B, if I is not A, and here if I is not A and J is not B. I think that this code is harder to understand, but hopefully correct now. If you want to understand it, I think it's better to first erase those ifs and focus on what you have without them. Okay, done. So this is still such a well-known problem that I will talk a little bit more about this visual aside. So the solution, if you have two strings, let's say something x, y, z, and let's imagine this fake dot, and there is some other string here, maybe not a, b, c, d, e, f, x, z, y, and so on. You make a rectangle out of it. That's our DP table. It is size of it is equal to length of one string plus 1 by length of the other by 1. Any state here, any cell, it represents what is the minimum number of moves so far if you dealt with things before this character and before this character. So you dealt with those prefixes already. What is remaining is to transform yz into that. This is your remaining goal. And your possible transitions are to the right by +1, to the down by +1. Those represent insert or erase. And diagonally, where it's either +0 or +1, depending on if those two characters are the same. We're looking for the optimal path from one corner to the other. So this path might maybe look like this. And mainly this optimal path will automatically try to find moments where we have equal characters. For example, I'm guessing that here x is equal to x, so it might be optimal to get towards that cell with the +1 operations. Then from here we can move diagonally with a 0 cost operation. We just match them automatically. Then we are here, z is not equal to y, so we move to, we skip either one of those. Let's say we are here with the cost of +1. And then z matches with z, so I can move there with cost of 0. This is one optimal path. Another one would be here, when you have a choice between y and z, you can go right, so skip the z, and then y is equal to y, you are here and you have the cost of 0 there, and you go down. You can, like, later rewatch this part of the video and analyze what operations of insert and erase those two optimal paths represent. This one in blue-yellow versus this one in blue. They have different ways of dealing with how we transform xyz into xzy. Is there any schedule for your streaming? It's not consistent and it will not be on weekends, sorry. I need to adjust to online competitions and also sometimes to my own stuff. I will try eventually to stick to some schedule for weekdays, but not this month. Maybe through the school year or academic year. Is it possible to get the number of optimal paths? Yes, but that's a separate, harder problem. Slightly harder. Okay, I've gotten accepted, right? Yeah. Then let's move on. The codes will be in the GitHub repository. In the YouTube video description, there will be a link once I push that to Git. Given two arrays of integers, find their longest common subsequence. I would argue that this should be before the edit distance problem because it's strictly simpler. We have two sequences and we want to find common elements. For example, here, let me see, 1 is common with this one, then 3 is common with this 3, and 4 is common with 4. So 1, 3, 4 is a common sequence. We shouldn't do things greedily because sometimes we don't know whether we should match this 3 with this 3 or this 1 with this 1, what is better. And we need to do things in order from left to right. But we will solve it the same way we did edit distance, which is, I will make a 2D table for that. So for this input. And maybe I want to insert table, let's see, 8, so like a 9, number of columns, number of rows 9, number of columns 7. Hopefully you see some stuff there. We have this sequence of 3, 1. A sequence is not really that much different from a string. 3 2 7 4 8 2 and a dot. Something went wrong. Why is it? Oh, I typed one digit twice. 2 7 4 8 2 and the end versus 6 5 1 2 3 4. You're looking for common elements. For example, 1 and 1 is common. You can think about it this way. If you have two common elements, 1 and 1, then you have here a coin. Once you collect it, you need to move on there because you cannot take 1 or 1 again. Also 3 with 3, this is there is a coin here. 4 with 4, there is a coin there. 2 with 2, coin. 4 with 4, yeah, got it. 7, 2 with 2, 3 here. Okay, you have some coins. You need to find optimal path, which might look, for example, it doesn't actually matter how you move through empty cells as long as you don't go back. But once you take something, you cannot take this or that again because that's already counted. So you move on. And here, I think this should be one optimal path. I can collect 3 coins, and those represent taking the 1, 2, and 4 in common. 1, 2, and 4 in common. There is additional another optimal path. That's to take this, maybe different color, this, and that. You can also move like that, and that would be taking 1, 3, 4. So just like in any distance, we have a dp of ij, and I will define it like max answer so far if we are now in cell ij, and that means, in other words, max length of common subsequence so far if we now look at a of I and b of j. This element from the first sequence and this element from the second sequence. We initially look at a of 0 and b of 0. I often in my head phrase the states like that because then it's more clear what transitions I'm exactly doing. And it's clear that we start from 0, 0. Why not 1, 3, 2, 4? Because it's not a subsequence. You cannot reorder elements. You have a subsequence 1, 2, 3, 4. You don't have 1, what did you say, 3, 2, 4. That's not a subsequence. If we could reorder elements, then sure, we could sort them and do something like 2 pointers, but the problem is about finding subsequences, which means that we find elements in order that happen to be in the same order in both. Okay, so this, and we will again stop with dp of size of one length, size of one array and size of the other. I'm going to copy the previous code, paste it here. We here maximize. We don't have strings, we have the 2 sequences. This is now max. This still is valid. Max not number of moves. Max LCS, longest common subsequence. It's strange to say max longest, but it's max length of common subsequence. Exactly. Max LCS of first I elements of A and first j elements of B. We have this. We don't fill as infinity. We can start with zeros because now we maximize. We don't need that. For all the elements, I'm here. And the main situation, the main possibility is what we had here, where if this, and we add +1 if they are equal. If they are equal, then I add 1 when transitioning. I get a reward. Also, I can just move down to right. We now maximize instead of minimizing. I think that's it. Oh, first of all, that's a very incorrect value. Second is that second thing is here. Oh, not the +1 here. You don't have a reward. We need to reconstruct the answer. Well, now I think this is correct. We need to reconstruct the answer. To find the example of this subsequence that is optimal, the main way to do it is so-called breadcrumbs, which is also called parent array. For every state, you want to remember from what state you came here optimally. You should think about it as if you did something like BFS or DFS or Dijkstra, when you have any graph algorithm, in a general graph. If you have a graph where from one node you visit the other, you save the information from where you came so that you could reconstruct it backwards. Example, if I have a graph which looks like this. I want to find a path from 1 to 6. I run, let's say, DFS. It's not the shortest path, just any path. I run DFS. From 1, I visit 2. So I visit 1, I visit 2. Then I remember that for 2, the way I get here, the parent of 2 is 1. This is the way I get there. Then from 2, let's say I visit 3. Then for 3, I remember my parent is 2. This is how I get there. From 3, I visit 4. For 4, I remember the parent 3. From 4, I visit 5. So from 5, the parent is 4. And finally, from 4, I visit 6. So for 6, the parent is 4. And now, after running this DFS, if you want to create or output the path from 1 to 6, you start from 6 and you go backwards following the parents, the breadcrumbs. For 6, the parent is 4. For 4, the parent is 3. For 3, the parent is 2. For 2, the parent is 1. So this would be the example path that we found. I look mad today. I would be surprised if that was the case. So that's what we will do here. So let's transform this. Maxi. So we have this. I will make a separate array, let's say. With parent or previous. So that for every cell, ij, I would remember what was the optimal previous cell. Now 3 times I will do it, so it would be nice to optimize that. So the function maxi I will make maybe here, and it will be responsible for also remembering the parent, the optimal previous state. What this will get is, let's say, it will know that if we transition from ij into i2j2, with the cost of operation cost, which will be either 0 or 1, it will do this. If dp of ij plus the cost, if it's greater than dp of i2j2, if this is now optimal, then dp of i2j2 is equal to dp of ij plus cost, but additionally, parent of i2j2 equals ij. So this is the new thing. And now we maximize from ij, we move to I plus 1, j plus 1, and I have this cost of whether 2 elements are equal. Then if this is the case, ij, we move to ij plus 1 with the cost of 0. Cost of 0. We output this, sure, but now we need to run the breadcrumbs or parent array. So I start from, let's say, AB, or let's just use A. No, let's do this. While they are positive, So while we're not at 0, 0 state, I move backwards, which is I and j should at the same time move to parent of ij. What's the way to untie? I don't remember. C++ untie pair. Are those new variables or? Let's do it. TMP is this. Two lines instead of one. And as we go, we need to also save the elements. And so if for those operations where we actually have equalities, we need to detect that and output them. For now, let's say if a of I equals b of j, then output both. Outputs what they are. This will not fully work, we will see why. Additionally, I start from values that are outside of the array size, so I need to, before I check a of I and b of j, I need to check if they are even in bounds. And I think what we will see is something very, very similar to the correct output. Four to 1. What I got is the path backwards, but I want to print it not backwards. So I collect the path. Here, don't output, push back. Then reverse. And for every element of the path, output it. Now it's correct. 1, 2, and 4. Submit. I guess that longest common subsequence, also that at distance, it requires a separate video. And I would actually say the same about this breadcrumb. But here it's a stream that lasts 2 hours. And I'm doing something wrong. Oh, that's only this is allowed when I move forward with both I and j. So that's additional if. A little bit annoying. I should have done something differently here maybe, but let's fix it there if we have this code already. So only if both are different, if I, so maybe, I'm moving from ij backwards into here. If this plus 1 equals I and this plus 1 equals j, and a of I2 is equal b of j2, then do this. Because a moment ago, when I had two equal elements like 1 and 1, of course, when I move forward from both of them, so I move to indices I plus 1 and j plus 1, it's correct that I collect this value 1. But also when I do those operations, so when I skip one of them, this also triggered, and some elements I repeated too many times. And I never change. So it was infinite loop a moment ago. I don't know if I needed to click that. Is it possible to use recursion in main function? Yes, lambda functions are possible. And I got a warning, but the correctness is there. Now, what can be improved here in this code before we move to another problem? I think that, well, I used here the push method. That is, I looked at state dp of ij and I move forward to those. I think the pull method actually is slightly more convenient here. So maybe it's a good idea to rewrite this code. How much time do we have? Yeah, I think it's worth it to rewrite. So, or another video. There are too many there are too many problems in this category. Push method. Code could be simpler with pull dp. I will just leave this comment and yeah, another day. Rectangle cutting. There is an A by B rectangle calling main inside the program undefined behavior. Did I do that? What do you mean? I only defined main. I don't know what you're talking about. I don't have another occurrence of mains. I never call it. Given an rectangle cutting. Given an A by B rectangle, your task is to cut into squares. On each move, you can select... no, I didn't call main recursively. I thought that the question earlier was to use recursion inside of main. That was different question slightly. Each move you can select a rectangle and cut into two rectangles in such a way that all side lengths remain integers. What is the minimum possible number of moves? Example is 3 by 5. So rectangle cutting. We have a rectangle of some size. 1, 2, 3, 4, 5. I can cut and I want to get squares. For example, I can cut here. That's the first cut and I have a 3 by 3 square. I can cut like that and I have another 2 by 2 square. I cut here and with this third cut I'm done. I got only squares. Though it's not necessarily optimal to get to always just cut away your square like that. I don't know if this is a counterexample, but if you had something of size, let's say 11 by 10, if you cut away 10 by 10, then you're left with here with 1 by 10 stripe and you need to do a lot of cuts. Instead, what maybe is better, I don't really know if it is, but maybe if you have 10 by 11, maybe it's better to do some other cuts that look more like this and then do something more strange here, and maybe this is then optimal. I don't know, but I'm guessing that no greedy solution here works. So if we cut, now for maybe the first time, we're not doing anything from left to right because we don't have a sequence in the input. We just have this figure, this drawing. But after we cut, let's say I'm doing a cut like that, it's not necessarily that I get a square, but I always get two rectangles. In this case, 1 by 3 and 4 by 3. Then if I consider this cut, I wonder what is optimal answer for, or what is the answer, the smallest number of cuts for this smaller rectangle and for this smaller rectangle. That's perfect example of the DP usage, where we have smaller subproblems that are identical to the original one. Possibly, DP of 3 by 5 rectangle is equal to number of cuts we need to resolve the 1 by 3 rectangle plus number of cuts needed to do this one. The order of dimensions doesn't matter. I can type this, I can cut it the other way around. Plus I did one more cut here. It's the blue cut that I started with. So I possibly do one cut and I'm left with those two. Whatever is the answer of them, the smallest number of cuts, I add those up. Now, it's not true that this is equal to exactly that. It's one of many possibilities of how we cut. So actually, I minimize with that. Because the rectangle of size 3 by 5, it can be cut here, 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 4 possibilities, and also here. 6 possibilities in total there are to cut such a rectangle. So yeah, we will simplest possible definition. If you're given AB and you need to compute the answer for them, dp of AB is answer for rectangle AB. There cannot be anything simpler for the DP state than exactly what the problem asks us to do. As the answer, I will output this. Maybe I will call those uppercase because I will iterate through the lowercase. For all possible rectangles, I will consider all possible cuts. For example, if there is, let's say, 3 by 5, I can cut it into 1 by 5 plus a 2 by 5. That's a possibility. The way to do it is something like this. You iterate how many of the A, let's say, rows, how many of them will be in the top part. And you say minimize dp of AB with dp of I by B plus dp of the remaining. If there were that many rows at the top, then there are that many at the remaining bottom. And we have one extra operation because we have just cut. Like in previous problems, this is a helper function. We do the same with the other dimension. We cut the first I columns, and then we have some number of remaining columns. What do you want? DP. Two-dimensional array. Because we minimize, it needs to be filled with infinity, otherwise everything would remain 0. I'm using size of the array a plus 1 because at the end I want to get access to element a itself. So indices need to go from 0 to a. And there is a case where the answer is 0, that's a square. If a equals b, dp of ab is 0, and you can continue, you don't need to, doesn't matter. Those things wouldn't do much anyway because 0 would stay 0. Correct here. Let's also discuss the time complexity. Accepted or not? Accepted, yeah. I have a times b, and here I have a for loop of size a and for loop of size b, but those are not nested, so those two I do not multiply with each other. But a times b times I repeat this, which is a operations plus b operations. So time complexity is a times b times a plus b, which is, well, roughly, let's say, O of n cubic, where n is length of a string. N cubic is fine if n is up to 500. Why use vector and not to the array? I can ask you the same thing. Why array? Vector is nice, modern, I can easily fill it with infinity. It's good to use vectors. Unless you talk about array that you write like this, then yeah, such array is okay. But array that you do here with constant size, that mainly has disadvantages. For example, it's more annoying to fill that with infinity. And generally, global variables have some downsides. William solved the CSES problems in 12 hours. That's reasonable. That being said, there are new CSES problems. I don't think now it's possible to solve all in 12 hours. Even if you knew all the solutions, I think just typing those 400 problems here, there are 400 now, not 200 as it used to be the case, that's too much typing. Maybe it might be possible to estimate how much time you would need with 100 words per minute. For big sizes, vectors and arrays are the same speed. Okay, and by the way, here we used pool dp, where I iterated the state and then this dp of ab I here computed, because it was natural for me to think, if I have a rectangle, how I can cut, And to compute dp of AB, I need to pull the value from other dp states. It's not that here, when I'm there, when I'm here, I already know dp of AB in advance. No, I'm here to compute it. Why memorization is not passing here? Maybe because it's slow. Recursion is slower than iterative methods. In competitive programming, you want to do iterative solutions. The case where I would use arrays instead of vectors if I had a lot of small arrays. For example, this thing, let's say n by 2, this is way more efficient than same size vector, because this means create n arrays of size 2. And that will just take n times 2 memory. If you create n vectors each of size 2, that's not efficient. It has big overhead. So in such a case, if I cared about efficiency, I would use an array over a vector. Codes will later be in the GitHub repository. Reminder, I started 2 weeks ago group classes. Consider joining. Every week I choose nice problems from old competitions. We solve them. There is a Division 1 and Division 2 groups. So there's something for everybody. You can ask questions, so I think you will improve in the group. No, I don't know that, Tony J. But maybe because of the costs, it was hard to get to the IOI. Task number 13, if you also count yesterday. Minimal grid path. You're given a square n by n grid where every square contains a letter. You should move from the upper left square to the lower right square. You can only move right or down. What is the lexicographically minimal string you can construct? Can you solve this without hashing? I don't want to do an overkill, so let me quickly check. But my solution requires some string algorithm like hashing. And what is this website? This is normal Yusaku guide? Why is it in white? So where I'm used to it being black, and on my, am I here logged in? Why does it settings? Okay, system. Okay, I see. So in Linux, I have not set up my system to be by default Dart background. Anyway. Oh, it's not this task. Minimal grid path. There are greedy solutions? Really? So we can move diagonal by diagonal. Okay, fair. That is though very advanced compared to other problems here. How much of that do I want to explain? This is just such a jump of difficulty compared to the previous problems. I don't like it. Let me quickly look what will be the next tasks. That's I don't know, maybe those will be bit sets. Removal game, that will be trivial. Okay, well, I want to do things in order, so I will not skip this. I will describe briefly the hashing solutions. Then I will code that diagonal solution that is described online. That being said, it's perfectly fine if you do not understand the solution to this problem. It is just way more difficult than others we are discussing today. And that's just some, I guess, not the best aspect of CSES, that you have such inconsistent difficulty. But well, I don't want to simply skip it. So, I don't know why that tutorial online mentioned greedy. I don't think that there exists a greedy solution here. This is minimal grid path. So it says find lexicographically smallest string in a grid as you move from the top left corner to the bottom right corner. When you start here, and let's say you start with character X, when you have A and B, when you have a choice between them, you always will go to the smaller one, because you minimize the string that you obtain. But the tricky thing happens if you get two same characters, because your choice should depend on what is available later. Maybe here is A, here is B, and here is B, then it's better to go right. But you don't know that only looking at those two characters. Also, it can be more complicated, because maybe to choose between those A's, you need to consider what is later, what is here later, and maybe just after that, at somewhere there is a character that is better than others. It's, by the way, clear here that diagonals might matter, because always at ith move you're at the ith diagonal. But first, let me describe a hashing solution, or let me try to describe it. We'll see if it even works. So in order to decide if I should go down or right, actually I should already have information about what happens next. Because of that, we will move backwards, because when I have the, let's say here, the target cell, and I know that for each of the neighbors I just go there, but now when I'm here at this cell, I can make a choice, go down or right, based on what I see. And here I should go down. Let's say this is C, this is C. Now when I'm here, I can make a choice of going right versus down based on the DP values for those. For this C, I know that I will go right and I will create CAX. For this C, if I am there, then the only possibility for me is to collect CBX, and that's worse than CAX. So this is better. From that, a solution that turns out too slow is dp of ij is best, so lexicographically minimal string from cell ij to the end, to the bottom right corner. Then the transitions are that dp of ij is equal to the character that is here plus the minimum possibility among my bottom neighbor and my right neighbor. Among those two, I choose the smaller lexicographically string and I add the character that is here. And at the end, the output will be the dp of 0, 0. Sadly though, it seems that we have n squared state as always, but when doing this transition and when assigning, we copy the n characters, so it's times n. The total time complexity of this dp solution is n cubic. What you can do instead of that is keep the strings in more compressed form, and I wanted to do hashing there. Actually, I don't know how to do it without some persistent structures. So I think that solution we need to drop completely. Yeah. Well, I will discuss the non-hashing solution because that thing works. I don't know if there is a way to quite easily optimize this to close to quadratic time without something very heavy. So what I have in mind is persistency plus hashing. Zikrus did, so what did you do exactly? What I'm describing, which is persistency with hashing or something else? With hashing and some data structure like segment tree, sparse table, we can in logarithmic time compare to strings. I just don't know how without thinking about it persistently to copy the structures around. Linked list with binary jumping and hashing. Okay. I would say that's not far away from persistency. Nikos, I will only say that you might want to switch to AddCoder DP contest because those tasks are slightly easier. Yeah, persistent. Yeah. Okay. But that sounds like CSES. The fact that you did something with this extra log factor and it was complicated solution but reasonable time complexity and you got time limit exceeded. I'm not surprised. Okay, instead what we will do is the following. When for this, I know that this cell is better than this bottom one. CAX is better than CBX, and I actually don't need to store those strings. It's enough for me, when I look at those three characters C, to know that because those two here, they lead to an optimal string CAX, they are better. So let's assign a hash of 1 to them. This is 1, this is 1, and this is worse, so let's assign a value 2 to it. You can think about it as something close to coordinate compression or index compression, but instead of changing values into smaller values, you change strings into small values. Also, we can call this perfect hashing, where actually there is no hash collision possible. Perfect hashing is possible in some data structures, like you can build sparse table with perfect hashes, but that's not the topic for today. Got accepted with BFS. I see that you keep mentioning BFS, but how do we do it? And what is the time complexity? Because it seems to me that BFS, however you do it, it will be n cubic. So can you tell us how you did it? My guess is that there are weak tests and this is how you got accepted, but maybe there exists a solution with BFS, and if so, I would want to read it. So please describe in the comments, I mean in the chat. Okay, so we will do this perfect hashing. We need to think about how to transition from one diagonal to next. So if I know that for a diagonal, there is here value 1, value 1, value 2, and those represent the relative order of how good those strings are from here to the end. So those two are equally good cells. When I consider those cells and I want to compare them, first of all, if one is X and the other is Y character, then X is better than Y. It's smaller lexicographically, so it wins. But from X, if I have a choice between 1 and 2, then 1 is better. What I'm going to create is simply pairs of character comma int. For example, for this X, its now value is equal to a pair of X character and a 1, which is the minimum of this versus that. So this is the value here at this X character. If I put an X here, its value is that we start with X and then I have a following string with the relative value of 2. For this Y, I have Y comma 1. And here, let's say there is a Z, I will have a Z comma 1. Now, this trick, what we're doing isn't really DP knowledge anymore. It's a knowledge of comparing strings, let's say, this perfect hashing. Now, what I will do, and this can be done in linear time, but I'm not going to, is I will just sort those pairs. So looking at diagonal with k elements, sort those k pairs, and this is your new relative order. In sorted order, when you sort those 4 pairs, this is best, so I will assign 1, second best I will assign 2, third best, fourth best. If this was instead character y, then we would get a tie here, and this would be tied at value 3. Again, think about it like coordinate compression. Some values are equal, so they get the same smaller value. And those are the values from the next diagonal. Those values themselves, they do not give you the answer, but they allow you to compare in constant time. So now once you are done with the full thing, you need to reconstruct the path, to do it, let's say, backwards, but you are doing this DP in this direction. So now backwards in this direction, you will do breadcrumbs or something similar to it. You start with top left corner, you have some character there, let's say C, and always when you make a choice between going right and down, you compare the 2 relative values. If one is 1 and the other is 2, you choose the smaller one, and that's it. If there is a tie, you go to either. Yes, this is one node program to draw. So eventually we have a very simple solution. By the way, very hard to come up with. Again, even though the code will be simple, this is the hardest problem today, I think. Even for somebody experienced, they can struggle to come up with this idea. And they can instead go to my first idea as well, which was to do something with hashing and persistency. So now to code it. I need to iterate diagonal by diagonal. Diagonals are described by the same sum of row plus column. I will now iterate all cells with the same sum of row plus column. If I know that row plus column should be equal to diag, the sum, then column is equal to diag minus row. If it's in the bounds, then this cell exists. Here I found all the cells that have the same sum of values, the sum of row plus column. The bottom right corner has coordinate n-1, n-1, so its sum is 2 times n-2. That being said, I'm not sure if we want to even consider it, because there is nothing to relatively compare it to. So maybe I will change those bounds in the future, I'm not sure. Yes, Yuxi, you are correct. We build this DP backwards because first we start with the bottom right corner because there is nothing to do there. Then for its neighbors, we know what is their optimal moves and so on. What we cannot do is start from the top left corner because we have no way of comparing. The solution for bottom left, for top left corner, so for the starting cell, it depends on what we computed for everything else. So this is the way to do it. So the DP of 0, 0, it depends on us already computing DP for other cells. Now, I need to, for every cell here, look at its possibilities of going right or down, and from that create a vector of pairs, character, comma, int. Let's additionally create the variable for the size of them. I have k cells, let's say, in this diagonal. For each of them, there is row column, that's v dot first, v dot second. I take minimum of right neighbor and bottom neighbor as long as they exist. Also, I will have that dp of n by n. Maybe for the first time, let's not call it dp, let's call this hash. Will this compile? Will this let me call it hash? Yes, v of I. And now there is some annoyance here with us sometimes not seeing the bottom neighbor, not bottom or right neighbor. I'm going to hack this by adding a fake row and fake column to my grid. And its hash or relative value will be infinity, which is very bad, and we never want to use it. Actually, infinity equal to n would be enough, but this is good. So always when you compare between a real cell and this fake cell with infinity, you prefer the real cell, and you will go there. Thanks to that, I'm avoiding here ifs. I will always say that the value is minimum of dp of row plus 1 column and dp of row column plus 1. So this is this optimal following string. And then I have my own value, which is that's a of row column. This is a pair of character, comma, integer, like I described with a drawing. State, value. We have this. And I want to do something, again, equivalent to coordinate compression. So I will say order and place back state, comma, index I. I need to keep the index to know it's the relative order of what. Let's call this coordinate compression, kind of. dp not declared because I called that a hash. Sort. In this order, do coordinate compression. Let's use values starting from 0, whatever. If I, or from 1, if this is 0 or order of I is different than the previous one, again, this is just coordinate compression. If there are equal values in a row, they want to get the same value. Now we need to unpack what is the row and column here. I guess here I don't really need the index. I can directly put the coordinates. So now what we have here is the pair from the drawing with current character and the int describing relative hash of following string, comma, this is the coordinates of this cell. So now I need to unpack order of I second, and the hash value of row column is equal to next. Okay, now it doesn't hurt that we do this for the bottom right corner. Yeah, it doesn't. Finally, let's create the answer. While row smaller than this or column smaller than that. I have a choice between going right and going down. If hash of down smaller than this, then we go to this value because it's smaller, row plus plus, else column plus plus. As we go, let's output the characters that we see. We also output the starting one and a new line to make it look nice. Yeah, that works for the sample test. Time complexity should be clear. It's well, no, okay, not that clear. And I need to optimize my sorting apparently. For every diagonal, we iterate all the cells that belong to it, and in total then every cell will be considered once, and we sort those cells. So my time complexity is n squared times log of n. It seems that I'm too slow. 3000, 3000. So sometimes for 3000 I'm fast enough, but if sorting is not that trivial, then I'm not fast enough. I can work on a constant factor, or I can, why sort? Because I want to know in this diagonal what is better than other things. I want to know, so this relative order. So that in the previous column I could make choices, and thanks to that in the previous column I could make choices. We can here not rebuild always. Can I copy this to actually optimize locally? Test input txt, test input txt, test input txt. Let's see how long this takes locally. 800 milliseconds. I don't like those tight limits in CSES, and apparently my PC is faster than their judge. Okay, some small optimizations is that I will not emplace back here. I will choose the size first, and thanks to that I will just say order of I is this pair. Is it faster? No, still 800 milliseconds. If I sort multiple times, will this significantly increase the runtime? Yes, it did. So this is at least partially bottleneck. By the way, sorting already sorted sequence is usually faster because there are some ifs for that. If I here return, does it change anything? Not really, so this part is fast. What about the reading input? Oh, this takes a lot of time. Okay, I found the issue. Reading input needs to be optimized. There are two magical lines that you should use with sin cout if you use those. And now the total speed got down from 800 to 500 milliseconds. So the issue wasn't maybe with the constant factor or time complexity, it was with just the way I read the input. Scanf would be faster. It's faster, but not enough. Well, I can sort in linear time because other than infinity I deal only with relative values from 1 to n. That's one possibility. n placed back in V. I can also go once and count how many cells there will be, but I don't think that optimizing this with predefining the size will matter that much. Yeah, putting return statements to very quickly figure out the speed of some part is a nice skill in competitive programming. Anything cache related that I should optimize? I think that sorting is the significant part. Now this will be very messed up, but if I remove the sorting, Yeah, then it's significantly faster. It seems that sorting is the part we need. Oh, I know one more issue. We are sorting very heavy objects. It's so much data. Character, int. Actually, earlier I had here the index only. That would be faster. So I can replace this with integer corresponding, or just let's say the row only. Actually, I wonder, from curiosity, if I here only put the int and I here only pass the row, because it's easy to reconstruct the column. I have row is order of I second, column is diagonal minus row. Is this faster? Just slightly more compact. Yeah, from 500 something to 480. Let's submit, why not? Still not good. I can compress this pair into one int if I want, because maybe it takes a lot of time for it to compare first by character, then by int separately. If character is from 1 to 26, the int also is very limited. I can compress it more. Also, the infinity I will replace with n. There are never more than that many cells, or maybe n plus 1. There are no more than that many cells in one diagonal, so I will not use extra infinity. And now this state I will compress to a single int, and that will be equal to a of row column, the character, which is more important. Now it's a value from 0 to 25. Let's multiply it by n plus 2 and add this thing. This is how you compress two values into one. State. Now this gets compressed into integer. (400 milliseconds). So it's better. Okay, accepted. Still though, because the values were from 1 to n, and even with the characters still it's small enough, you could do it in linear time. I just didn't want to bother and do a lot of extra code. I don't think that array of int comma 2 would be faster than a pair. A pair doesn't have an extra overhead. What do I use for measuring runtime? The command time in Linux, in Bash. And no, the greedy solution does not work here. If you have ties between characters, you would need to look forward, and that's very complicated. Okay, is there analysis? Yes, there is one. Are they describing something greedy? Because the code seems very fast. Official editorial. There are that many rounds that construct the minimal string corresponding to a path from top left square to the bottom right square. Maintain a prefix of optimal string in this process. The prefix is extended by adding new letter. Move one step right or down. What? What's going on here? We go forward? And so it's not a DP. For every diagonal, I think I get the idea. We know what character we print now, but we don't know where we will be, and we maintain information about it. Okay, it's something like DFS that will propagate. Okay, I got it. So here's the official intended solution in linear time. If you see here A, then you see x, y, then, well, you know x is better, so for sure you will go there. And you already print A, you already print x. Now, if you see here B and B, then you print b to the output. But in your program, you keep information that now you're here or you are here. You don't know where. Those are both possibilities. What happens when you consider next diagonal is that you can be in one of those three cells. Among them, you find the minimal character. Let's say that it's x, z, x. Then among them, x is minimal, so you will be one of those two, and you output x to the output. You print it. And you move forward, always remembering a vector of cells where you can be. That's a very smart solution. It barely can be called DP. It's a very smart one. I'm impressed. I like the problem a lot now that I know this solution. And I wish that I knew the solution before coding mine, because it wasted some time today during the stream where I wanted to do more of DP problems. How to improve at graphs? Solve graph problems. After you do 20 DP problems, 1600 rated, solve 1700 rated. Okay, so nice task. Not really matching others that we are solving today. How many do we have until the end of the category? We have 10 remaining. Now it's 30 minutes to the Code Forces Division 3 round. So I hope that maybe those three, which seem easier. I wonder how hard mountain range is. Well, let's go. We have half an hour. Money. Sums. Money sums. You have n coins with values. Your task is to find all the sums you can create using these coins. N is up to 100. The coins up to 1000. So the sum is up to 100,000. We care about a Boolean value. For every sum, we just want to know if I can get it or not. And for every coin, what I do is, if dp of some sum is possible, then dp of sum plus this coin is possible. And just like 10 problems ago, yesterday, we will do for loops backwards. We will do backwards so that we wouldn't from that transition to dp of sum plus twice the coin, because it's not allowed to take a coin multiple times, I believe. Not sure though. The time complexity, if we don't use bit sets, will be O of this sum multiplied by the number of coins n. Or in other words, the sum was n up times x times n. And that's roughly 10 million operations, so that's perfectly fine. After coding, I will also show how to optimize with bit sets to make it 30 times faster. Actually, more than that. It will be 100 times faster. But first this. I don't even need to read coins to the array, because I will one by one process them. Let's call this yes, like possible or visited. N times 1000 plus 1. That should be enough. Initially, you can get the sum 0. That's when you have nothing. For every coin, so repeat n times, read a coin. And for every sum, we need to do it backwards, otherwise you would incorrectly consider that the coin propagates a lot and allows to be taken multiple times. Starting from, like, let's say this. If yes of s, then yes of s plus coin is true. What I did here is, I know that the total sum will not exceed that. So without this coin, I need to have at most that much. So I would here transition without exceeding the bounds. Maybe something smarter and more flexible is the sum so far variable, where here we know how many at most we had from previous coins, and then we just add this. So it's like a prefix sum. And we know this here we iterate what is the sum of values of coins so far, and some of them we used, some not. So for sure, if the coins so far were, let's say, 5 and 7, then the most we could get from them is 12, and there is no point iterating more than that. At the end, you want to output the values. So for everything, if yes, you don't want to output 0 because they are not doing it. Does that work? After 9, I need a new line, and then I think we are good. Yep. This is of n squared times x. But after my submission, I will show you the bitset solution, though today it's not a lecture on bitset, so I will not explain too much. Just when you have a Boolean array, you can keep it in more compressed form of bitset or bitmask, and operations like those become bitwise shifts, which are very fast for a computer to handle. So this is, let's say, one valid solution, and the better one is that this can be bitset of size that much. Let's call this yes, and all of that is replaced with yes bitwise OR with yes shifted by coin. This means that every bit from here can get shifted to the right, or the index increased by that much, and those are also valid outputs. If you replace everything here with this line and this with that line, I think the code will still work. Should we just test it? But I want to leave this in the GitHub repository as something more valuable for the people learning DP. Let's have a test. Yeah, I think it works. You will not see big differences here in time because those values were small anyway. It was also around 0 earlier. Yeah, so we will not see really the difference, but I think that this should be around 100 times faster. Krish, you don't need to explain that you missed the stream. That's fine. But good to have you back. That was money sums. CSES is not better than LeetCode, it's different. LeetCode is for interview prep. CSES is a selection of problems allowing you to practice algorithms, mainly with competitive programming in mind. You selected the old file, oops. Oops. Good point. Thank you. Compile error. Okay, accepted. Yeah, but good that we checked that. It would be a little bit stupid to create a code and not even submit it. Do I have a Discord? Yes, I have. In YouTube description, it's not there. how do I give you my Discord? So you can retype this thing that you see from the Twitch comments. Hi, Brainard. Removal game, 15th problem in the DP section. There is a list of n numbers and two players who move alternately. On each move, a player removes either first or last number from the list. Their score increases by that number. Both players try to maximize the scores. What is max possible score for the first player when both play optimally? So if I always have a choice between first and last element, you might be tempted to say that greedily we take the bigger number. My first question would be, what should happen in case of a tie? And second is, even if this is big, maybe you shouldn't take it because you unlock something huge for your opponent. If you take 7, the opponent takes 100 and you miss on that. Instead, you should have taken the smaller value of 6 and wait for this 100 to be revealed. In particular, that would be the case, let's see, now? Yeah. If you here take a 7, opponent takes 100 and you messed up. If you take a 6, opponent will take a 10, you get 100. So that's better. So greedy solution does not work. In many problems in this DP category, we solve them going from left to right. Here, the process described in the statement doesn't go from left to right. It goes from the end and from the beginning, kind of at the same time or alternately. So always the state of this game is that some elements from the beginning and some elements from the end were already taken, and the remaining part of the game is here. So that's the state of this process. Turn by turn, always we have this. And we wonder what should be the score, optimal score for both players. When somebody sees this part, this remaining part, they will take first or last element, depending or comparing what is the remaining value. If I take this, then what will happen? What will be my remaining score on this part? So dp of ij relies on dp of I plus 1j and dp of ij minus 1. If I take the element at position I, then I wonder what is remaining state of the game and how much I take from it. Also, it's useful to notice that those two players are symmetrical, so we don't need to, in a specific way, distinguish them. So the dp can just be defined like this. If in remaining game on range LR, what is score of first player to move and second player? So whoever moves now will have that much score in total. That will be my definition. Read the input. Create the DP array. Longs I think are needed. And now for this first solution, I will use pairs. That being said, later we will optimize it. We will get a difference for some reason. I don't want to always type long, so I will just type LL. Let's say that by default those values are 0, 0. I don't think that matters because we will do pull DP. Like in the cutting rectangles, we have some possible choices of a move and we make a decision depending on what we see is the score for the remaining part. Now, the order of for loops here is not trivial, so we will fix them later. For now, let's say for L and for R, but it's very easy to mess this up, so we need to get back to it. dp of LR relies on, let's say, minimum or maximum of dp of L plus 1 R and dp of LR minus 1. Those are remaining ranges where the game operates, but it's not that easy. Also, if L is equal to R, then what we have is the first player to move now gets just x of L, and the second player gets nothing. At the end, we need to output this. Dot first, the first player to move has this score. What now? Well, if I'm the first player to move now, I take x of L. This value dot first shows me how much my opponent takes, because he is now the first to move. This is my score, my remaining score, because for this remaining range I'm the second player. So this plus dp of L plus 1 R dot second, that's my total score. And this thing I will compare with something similar from that remaining range if I take x of R. So this I compare versus remaining range dot second. So my score is, I maximize, so I take this or that. The opponent's score, well, if you have a range and all the values are taken, then if you know what one player scores, then the other will get everything else. So I will say that this is the sum of all the values in this range minus my sum. And finally, dp of LR is equal to this. This obviously is prefix sums. I'm not going to explain that, but you can look up what are prefix sums. They allow you to quickly compute sum on a range. What do you want? Okay, now the ranges. If I do this, it will not work, because we are not solving this problem from the beginning and from the end. We need to start from ranges of size 1, and we need to finish with this. This needs to be the very last state that we compute, because this one requires everything else to be computed. In particular, starting from L equals 0 is stupid, because this is what we leave for last. In order to go from small to big, either you need to make a for loop that iterates the size of a range. It's similar to how we did diagonals. You can here consider length from 1 to n, and here iterate only ranges of that length. But it's easier to do it in this way, where the L, the left bound, you iterate backwards. So you go from the end of the sequence, but the R you expand. This is the order where first we'll consider, let's say n is 5, or n is 3. We'll first consider range 2, 2, then 1, 1, 1, 2, 0, 0, 0, 1, 0, 2. So it's not perfectly from small to big ranges, but this is still correct, because always when you consider some range, let's say 0, 2, everything that you need is already computed. 0, 1 is computed and 1, 2 is computed. When you consider 1, 2 range with just index 1 and 2, no matter which element you take, the previous ones already are enough for you. Formally, what is required is range LR requires ranges L plus 1R and LR minus 1, because those are the transitions, and both are computed. This one is computed because we iterate L decreasingly. This one is computed because for the same L, we iterate R increasingly. So R minus 1 was before R. So this is good order, matching the order of transitions. If you really want to be formal and scientific with it, we want any topological sort or topological order of states if we say that transitions are edges. Eight indeed. Let's submit to see if it works. I see that there are 10 minutes to the code forces round. That's not great. Now, the slightly better solution in this problem is to realize that instead of caring separately about the first player versus second player, they are playing kind of the same game, where if he takes a 5, it's like me losing 5. So it's slightly easier to code and slightly more efficient to care about the value my score minus his score, and we maximize that because this is a single value and I can focus on it. This works formally because we are dealing with something called zero-sum game. You can read about it online if you search for zero-sum game. Zero-sum game is game theory, something that involves two competing entities where the result is an advantage for one side and equivalent loss for the other. If I take 5, I don't get access to it. The sum of points is known because if you have values 5 and 7, then in total you get 12, and from the 12 you get as much as you can, the opponent gets the rest. So you can also say that the DP is defined as maximum possible value like this. So I will say in the remaining game on this range, this is my score minus his score. Remember to register for the code forces round if you want to participate. There are 10 minutes remaining to the beginning of the contest. And now the prefix sums will not be necessary. The DP is just single long. This still applies. Now, if I have a single element, then this is my score and my opponent's score is 0. So let's say subtract 0, whatever. And here what happens is I can possibly take the first element, and then for the remaining part of the game, this value describes, now my opponent moves, so this value describes the first player to move score minus second player to move score. Let's say that this is 17. It's like negative 17 for me. So subtract. If his value of this difference is 17 from now on, then for me it's negative 17. Hence I subtract. I simply do maximum of that versus the other possibility. At the end, I don't want to print the difference of scores, I want to print my score. But I know if, let's say the sequence was 5 and 7, then this difference of score, my score minus his score, is 2, 7 minus 5. How I can get my score from that? Well, I know that my score plus his score is equal to 12. That's the sum of everything. If now I add those two things together, 2 plus 12, I will get 14, which is double my score. Just think about this as a system of equations. So the total score is 14, my score times 2 is 14, and this divided by 2 is my score. So I need to, this value, the DP value of difference, add to the sum of everything, the 12, and divide by 2. I will leave some explanation here. I will in a moment present one more way of thinking about it. But yeah, this is the last problem we're doing today. Accepted, removal game. So there will be 8 problems left for the last stream. That last stream will be in one of the next 2 or 3 days. Why now you did max? Because notice that I'm not doing dp of lr maximize with something. I'm just assigning maximum. This could not be replaced with maxi function. Okay, one last way to think about it is that when you have a sequence, let's say this, that sum is 15. By default, let's say my opponent gets everything, I get 0. My opponent gets everything. If I take a value, I really take it. It's +7 to my score. If my opponent takes a value, they prevent me from taking a 5. So it affects my score by +5. So both players just fight on this single score, the my score, and nothing else matters. Where if my opponent takes this, it affects my score by -5, my possibility of the final score. 7 + 3 - 5. That's not a great explanation. I see a better one. Is there a greedy solution? I'm not aware of any. Something similar to what you're suggesting, I coded first. I never distinguish between top-down and bottom-up. I found those terms very confusing. I use push DP, pull DP, and sometimes recursive. And this is always how I teach people. Push versus pull is important distinction. Because actually, bottom-up, in my opinion, is incorrect because the iterative DP you can do both ways. You can do it top-down, you can do it bottom-up. And I don't think people realize that. Okay, one last chance to register, or maybe not, in time. I actually don't remember until closing this. Oh, you don't need to register here because there is no hacking, right? Okay, still 5 minutes to the beginning of Division 3 contest. So I will just leave you with this. There is a way to think about it as the sum of all numbers initially belonging to one player, and both players just fighting for what the other player can collect out of it. Now this is done. We have solved several problems today, so that's nice. Struggled a little bit with one of them. Surprised me how hard it was, the minimal grid path. 8 problems remaining for the next stream. Keep in mind, or be aware, that I started the group classes. This is the link. Go read about those and consider joining. Every week we're solving problems, and I choose nice problems, then next week we discuss them. It's a private Discord server with a private Codeforces group. If you're not joining that, then still I'm making some streams from time to time. Thank you everybody for watching. Hope you learned some DP today, even though in some problems it wasn't that much about DP, it was about other things. I think that's fine. Among remaining problems, there are some that are difficult, like this tilings, the elevators. So the last stream, I think, will be significantly harder. Not for beginners, let's just say. I think, judging from the number of accepted, still there are 1, 2, 3 easier tasks. Well, increasing subsequence is just a well-known task. Good luck in the Codeforces round. There is a small chance that I will make a stream to discuss solutions. How long is the contest? 2 hours 15. No, there is no chance. After 2 hours and a half, I have something else to do. So no. Another day, maybe I will solve that. So maybe in a few days. Okay, thanks again, everybody. See you another